Hi guys, how's it going? Terry Brown, Mechanical Engineering here with another engineering mechanics video. This time we're going to look at a simple rigid body equilibrium problem. So let's have a look at the problem. Okay, so here's the problem and we're being asked to find the reactions at the supports after drawing the free body diagram. Okay, so hopefully you would have been told that drawing the free body diagram is the most essential first step in solving any equilibrium problem. So that's what we're going to do first in this problem. So the first step in drawing a free body diagram is to identify the body that you're going to analyse. In this problem, it's pretty easy. We're just looking at this single beam-like component here that's got supports at B and C and a load applied over here on the left-hand end at A. So yeah, we can just draw a simple rectangle, add some dimensions for reference. So we'll need those when we start to look at some of the moments. Okay, so when I'm drawing my free body diagram and starting to put on the forces and or moments that act on the body, usually I'll start with the applied loads. Because I don't have to think too much about those. We just got to look at what the problem is and add them on. And then we need to then go and look at our supports. So I've just put 30 degrees on there. So over here at point C, we've already seen come up here the reactions. So why have we got these reactions that are shown here, a horizontal force and a vertical force? Well, we look at the type of connection that it is, and we see that it's a pin connection. And we know that if it's a pin connection, that will prevent this body that's attached to it from moving in a straight line. Okay, so we can't translate the body at this point. It can rotate. So if I take my pen here at point C where I'm holding it, the pen or pencil is free to rotate. So there's no moment reaction there, but I can't pull it in the horizontal direction and I can't move it up in the vertical direction. So that means there must be force reactions there. Okay. And then next we've got our support at B here, which in this problem is just a roller. So here we think about what motion is allowed and what's constrained by the support. So here we've only got a vertical reaction. So that's telling us where that support is. The body that we're analysing can't move down. It's kind of understood that it's preventing it from moving upwards as well in a simple problem like this, but for now we can say, look, it can't move down, so therefore we've got a vertical reaction force acting upwards. It's free, so if you're looking at me in the little picture in the right-hand side, hopefully you can see this well enough that I'm demonstrating there with my pencil. So it's free to move horizontally, so therefore there's no horizontal reaction force there. And it's also free to rotate about that point, so there's no moment reaction. Okay, so that's how we go about determining what reactions we put at the supports. You would have seen in lectures and videos on modelling the supports in rigid body equilibrium problems. There's a table of about, I don't know, a dozen, 12 or 15, something like that. Students look at that and think, oh, do I have to remember all of those? Well, these days you've got usually open book exams and you can look things up, so you can just look it up. But if you don't want to have to go back and look it up and just remember how to do it, you do it by thinking about, as we've just done, what motion is free and what motion is constrained. So if it's free to move in a certain direction, so if it's free to rotate about C, then there's no moment reaction. If it can't be moved in a certain direction, then there's a reaction there. So there's a horizontal force and a vertical force. At point B, it's free to move horizontally there. Okay, you can just roll along, assuming friction is negligible. So free to move along in the horizontal direction, so no horizontal reaction force. Can't move downwards, so that motion is constrained, so therefore there must be a force there. If I had a built-in beam and I pushed it like this and it can't rotate now, then I would have to have over here a moment reaction. Anyway, so that's our free body diagram, including all of our forces with arrowheads on all of the unknown forces. So now we need to start putting in some labels on these unknowns. So we'll label the body ABC at the points of interest, and then we start to label our unknowns, because we'll need these to put into our equations of equilibrium shortly. So you may see in other people's examples online, YouTube examples, or even in the textbook, that they will call this maybe just B or BY. I prefer to use capital R with a subscript B and then Y. So this fully describes unambiguously what this unknown is. So it's a force or a reaction force. It's at point B and it's in the Y direction, which I haven't yet put coordinate system on. I'm not sure if I do in the solution later on, but at the very least, when I write my equations of equilibrium, I'll indicate clearly what the Y direction is. Okay, so over here at C, so for example, here some people might just call this CX and CY. Again, I prefer to call that F subscript CX, or in this case here, I've written R, capital R subscript CX, just to be completely clear and unambiguous that it's a force that I'm talking about and not a distance or whatever the case may be. All right, so I've just gone on to the next page and just repeated my free body diagram for reference, so you don't have to redraw your free body diagram. And now I've put on my coordinate system to show what, to clearly show what I mean by what is X and Y. And I've also now put on here what I'm going to assume as positive for the moments. And in most of my problems that I do, I'll assume anti-clockwise positive, because X and Y are usually like this. They could be rotated, but usually the Y-axis will be 90 degrees anti-clockwise to the X-axis. And if this is what I'm using for X and Y, then to be strictly correct, anti-clockwise is positive for the moments. Okay, so let's continue on with the problem. So now we need to start using our equations of equilibrium. Sum of the moments equals 0 and sum of the forces equals 0. Usually we'll start with a moment equation, because that usually will enable us to find one of our unknowns directly and remove some of our unknowns from the problem. In this one, we could have just gone straight to sum of the forces in the X direction, and we'll look at that in a second, but we'll start with a moment equation. So I've written that out here, the general moment equation, sum of, so the complete writing of this equation, capital sigma to indicate sum of, capital M to indicate the moments, anti-clockwise is positive, and very importantly, we need to have a subscript here to indicate where we're taking moments about. Okay, without this little subscript here, you can't check what the equation or whether the equation is correct or not, right? You've just got to guess and try to, oh, have they done it about here? Let me see these distances. I'm not sure, right? When you put this subscript here, straight away the reader knows, right, I'm working out moments about this point here, C. Okay, very important. All right, so we're going to use Varanon's theorem, or the principle of moments, and break this force here up into its components, vertical and horizontal, and find the moments of each of those components, rather than trying to work out the perpendicular distance between this 400 Newton force at 30 degrees to this point here, C. Now, we could do that. It's not too difficult, but it's a little bit more difficult than finding the components of the force and then using the perpendicular distances of the components. Because usually in a problem like this, those distances are already given in the problem. Okay, so looking at how this is defined, we've got 30 degrees here defined between this force and the vertical direction. So this component here, or this side, is the adjacent side to this angle, so it's 400 cos 30. If you need to go back and review your trigonometry and Pythagoras theorem, then make sure you do that. You should be able to make use of that and find components pretty quickly. All right, and this component down here is 400 sine 30. Right? So this side of this triangle over here is the opposite side to this angle 30. Right? So that'll be 400 sine 30. Note that I haven't put my component up here. I haven't drawn the component of the force up here, right? Because that indicates that its line of action is up here, and if we're calculating moments, it's kind of misleading, right? Same as if I haven't put my vertical component out here, okay? Because that kind of indicates that it's at a different distance to point C than it really is, right? So if you're used to drawing your components of forces, right, around the triangle, try and get out of that habit now. And draw them like this instead. Okay, so that's some maths out of the way. So now let's start to look at calculating the moments of the forces. So we've got the vertical component, 400 cos 30. Its perpendicular distance is the distance here from A across to C. And that is a total of 3 meters, so we can put that in. Now what we need to do is think about, is this tending to rotate object or the body clockwise or anti-clockwise? So if I hold it at C here, if I push down on the end where the 400 cos 30 force is, tends to rotate anti-clockwise about point C, right? I push down here and that causes an anti-clockwise rotation. If you just look at me in the little corner off to the side, little picture of me just off to the side demonstrating this. So if you're not sure, just get out your pen or your ruler or whatever you've got and just do this little exercise to work out which way the body is tending to rotate, and that will tell you whether it's clockwise or anti-clockwise. And then you need to go back and look at, well, what have you assumed as positive? Okay, so we've assumed anti-clockwise as positive. This force is tending to rotate the body in an anti-clockwise direction around point C. So this one remains positive. All right, let's go to the next one. Okay, so I've jumped across straight away to RBY here. Why have I ignored the 400 sine 30 over here? That's because, right, if we need to remember that when we talk about the moment of a force, it's the force times the perpendicular distance from the point that we're taking moments about to the line of action of the force, right? Not where the force is applied, but to the line of action of the force. And the line of action of this horizontal component here at A passes through the center of the beam, along and passes through point C. So its perpendicular distance is 0. So we don't need to include this force component in the moment equation. All right, so we've got RBY here tending or pushing up on the bottom of the beam. What's its moment about point C? Perpendicular distance is 1 meter. So again, we need to work out the direction of the rotation or the tendency to cause rotation. So hold your pen at point C, push in the direction of the force. So I'm pushing up at B, that's going clockwise. So that's going to be a negative moment. And then we get to our forces here, RCY and RCX. Their lines of action pass through point C. So their perpendicular distances to point C will be 0. So they don't appear in the equation. So we get one equation with one unknown, and we can solve directly for RBY. Okay, so let's just do some algebra, rearrange that, put the numbers into our calculator, and we get just under 1,040 newtons for the force RBY. Okay, so now let's look at using our other two equations of equilibrium. So as I said before, we can look at the sum of the forces in the x direction equals 0. Again, sum of forces, x direction, and an indication of which way is positive. Now, I don't need to put this arrow and this plus sign here if I don't want to, if I've got my x and y coordinate system defined somewhere else like this. So if we look at our free body diagram, we can see we've got RCX and 400 sine 30. Now, some of you might have been wondering already about the senses of these unknown forces that we've put on our free body diagram. I didn't talk about whether we put this one acting up or acting downwards, and whether this one's acting up or down, or this one's acting to the right or to the left. So you can have a look at the problem and you can try and work it out and draw the forces in the correct sense according to what's happening with the other forces and moments in the problem. But when you're first starting out with this, sometimes that's a little bit difficult. So you can just assume a sense, and then your equations and algebra and the final answer that you get will tell you whether you got them assumed in the correct sense or not. Okay, so here we got positive answer for RBY. So that positive answer tells us that we made the correct assumption about the sense of this force RBY. Okay, and this one's fairly obvious because, again, if we go back to, if you look at me in the corner, I'm not in the corner, off to the side, we've got our force, our pin at C here, and we've got our load at the end here at A tending to push it down, okay, and tending to rotate anti-clockwise. So we need that force at B for equilibrium to be causing a rotation or a moment in the opposite sense. Okay, so we can see that that's needs to be acting in the upwards direction. If we looked at it at the start here, we could have said, all right, we can see here that this force will have a horizontal component acting to the right. So therefore, this force here, we know will be acting to the left. Okay, so what we should expect when we do our equations and our algebra is that the numerical answer that we get here should come out as a negative number to indicate that this was originally assumed in the wrong sense. Okay, so let's do that and see what happens. So we have 400 sine 30 on the left here, plus RCX, no other horizontal force, so that's all equal to 0. Okay, so you can imagine if we had maybe 2 or 3 other forces acting on this at other angles, it might not be so easy as it is in this case, to just look at the problem and work out whether this should be to the right or to the left. Okay. So I've just shown you, I've deliberately chosen just to the right, just to show you what happens and that it comes out as negative in our solution. Okay, so minus 200 newtons, indicating, as I said, that this actually should be to the left. Now, what many students attempted to do at this point is to go back and change their free body diagram. Right? You should never do that, because all of this work that you've done here is based on what you originally drew on your free body diagram. So if you change your free body diagram, you've then got to go and change all of these equations, and that's likely to lead to errors. Right? So don't do it. Just leave it as it is. If you really want to end up with positive answers everywhere, start all over again, right? And work your way through. And that's probably a good check on your calculations anyway. Right? So, but yeah, never ever change your free body diagram halfway through because you get a negative answer, right? All right, so let's continue on. So now we look at some of the forces in the vertical direction equals 0. And we have our vertical component of our applied load, we have RBY, and we have RCY over here. So let's put those in. Yeah, so this force over here on the left at A is negative, and our other two forces here, RBY, which we now know from our previous equation, and RCY here, acting upwards, so that's positive. substitute RBY from what we got before, rearrange, and again we get we get another negative answer. Right? So here we've got minus 693 newtons. Okay, so I've just included in the solution here. So if you download, if you've got access to the PDF, if you're in my class, you can download the PDF with all of this here. So I've just written in here in my solution what I've just explained about the negative answers and the fact that you should never go back and change your free body diagram to match. Okay. Okay, so what we should now do is think about and check our answers and then round our answers to an appropriate number of significant figures. So we're going to check our answers first. And I do that on the next page. So I've just copied over my free body diagram again. Again, you don't need to redraw your free body diagram. It's already there for you. I guess maybe it's not a bad idea to redraw it on a completely blank piece of paper because you actually might have got the free body diagram wrong, right? And this check that we're about to do won't tell you that you got your free body diagram wrong if you use the same one. All right, so let's go through the check anyway. So now what I'm going to do is to just redo the problem and take moments about a different point. So here, this time I'm going to take moments about point B. Okay, again, very important that I've got as my subscript here, B, to indicate that's where I'm taking moments about. All right, so let's work our way from left to right again, like we did before. So we have our vertical component of the applied load, 400 cos 30. Its perpendicular distance now is 2 meters. So we've got that. Is it clockwise or anti-clockwise? I think we should be able to see without me demonstrating with my pen that it's going to be anti-clockwise again. So it's going to be positive. So let's move on to the next one. So RBY passes through point B, so that has no moment. And then we have RCY. So again, let's have a look and see which way this rotates. So if we had our, we're rotating about point B this time. So let's see about point B. So if we have our force down here of 400 cos 30, tending to cause an anti-clockwise rotation. And what we've shown over there is RC tending to also cause an anti-clockwise rotation. Right, so that's positive as well. Okay. So all equal to 0 now. So RCX has a 0 moment about point B because this line of action passes through point B. So rearrange that, solve for RC, and we get a negative number, minus 693, same as we got before. Okay. All right, so now some of the forces in the X direction. So this is going to be the same as we did before. Can't really change that very much. So now instead of using a second force equation, I'm going to use a second moment equation. So this time I'm going to take moments about point A and solve for, what haven't we solved for yet? RBY. Okay. So let's write our equations of equilibrium. So here we'll start with the moment caused by RBY. So this time the 400 cos 30 doesn't appear in our moment equation because it passes through point A, which is the point we're taking moments about. Okay, so RBY times perpendicular distance of 2, pushing upwards here to the right of A, so that's going to cause an anti-clockwise moment about point A. Okay, so that's positive. And we've also got RCY is our other force that we need to consider. RCY at a perpendicular distance of 3 meters, also tending to cause an anti-clockwise moment about point A. So another positive term there, and that's all we have. So put that equal to 0. Substitute in for our known value. Right, so here, right, if we go down here to the bottom of the page, RBY is now equal to minus RCY times 3/2. We've just rearranged that equation. And now when we substitute for RCY, we have to substitute the negative value that we got in here, so that we end up with a positive value for RBY. Okay? And this is where students get into trouble and make mistakes if they try and change their free body diagrams and make this positive. Okay, so as I said before, best not to do that. Just leave it as it is, leave the negative value there, write your equations of equilibrium according to the free body diagram that's drawn, and then when you need to substitute a value in, you substitute the negative value, if it was a negative value, into the equation here to get the correct answer. Okay, so in situations like this is where I see a lot of students make mistakes. Okay, so put that number into our calculators and we get 1040 newtons. So our answers match what we got before. Doesn't guarantee that they're correct, especially if you've used the same free body diagram, because if you have used the free body diagram could be wrong and you've just redone the equations of equilibrium and the algebra and matched two incorrect answers. Right? But it's better than doing nothing, and it makes you think about the problem again. And even if if you happen to get something wrong in here, you might go back and look at your free body diagram and say, oh, actually I got the free body diagram wrong. So yeah, just make sure that you do some checks and think about your solutions. The reason I've kind of highlighted this here is in students' assignments and quiz answers where I say, look, you need to make sure you check your solution. They'll say, oh, answers match, that means they're correct. No, it doesn't mean they're correct. It means it's more likely that they're correct, but it doesn't guarantee it. Okay, so writing our final answers and rounding to an appropriate number of significant figures. In most general engineering calculations and problems like this, we don't know the input values to any better than a few, plus or minus a few percent. So, 3 significant figures is really all you should be giving your final answers to. Any more than 3 and you're telling lies. You don't know the answer to that accuracy. Okay, so that's the end of the problem. Hopefully that was helpful to you and help you to understand how to go about solving rigid body equilibrium problems. So there'll be much more difficult ones than that you'll need to do, but this process that I've just shown you, that's the process you use for all rigid body equilibrium problems. All right, catch you in the next video. Bye for now.